In the vast expanse of the cosmos, where stars are born and die in cataclysmic splendor, there exists a phenomenon so enigmatic, so profoundly strange, that it challenges the very boundaries of our understanding: the black hole. These celestial enigmas, born from the collapse of massive stars or the collision of cosmic titans, are regions of space-time where gravity is so intense that nothing, not even light, can escape their grasp. For decades, black holes have captivated scientists, philosophers, and dreamers alike, serving as both a frontier of physics and a canvas for the imagination. Yet despite their prominence in both science and culture, black holes remain shrouded in mystery, their secrets locked behind an invisible veil known as the event horizon. In this exploration, we delved into the latest theories surrounding black holes, grounded in the most recent scientific advancements, to unravel the mysteries that continue to perplex humanity. The story of black holes begins not with observation, but with theory. In 1915, Albert Einstein revolutionized our understanding of the universe with his general theory of relativity, which described gravity not as a force, but as the curvature of space-time caused by mass and energy. Within a year, German physicist Karl Schwarzschild found a solution to Einstein's equations that described a region of space-time so warped that it formed a point of infinite density, a singularity, surrounded by a boundary beyond which escape was impossible. This was the first mathematical description of a black hole, though the term itself would not be coined until decades later by physicist John Wheeler. Black holes, as we understand them today, come in several varieties. Stellar mass black holes form from the remnants of massive stars that exhaust their nuclear fuel and collapse under their own gravity. Supermassive black holes, millions or even billions of times the mass of our own sun, reside at the centers of galaxies, including our own Milky Way. Intermediate mass black holes, a less understood category, bridge the gap between these two. And then there are primordial black holes, hypothetical entities that may have formed in the chaotic aftermath of the Big Bang. Each type raises unique questions, but all share a common trait: their ability to warp reality itself. One of the most enduring mysteries of black holes is what lies beyond the event horizon, the point of no return. The event horizon is not a physical surface, but a boundary where the escape velocity equals the speed of light. Anything crossing this threshold is lost to the outside universe, its fate hidden from observation. For decades, black holes have captivated scientists, philosophers, and dreamers alike, serving as both a frontier of physics and a canvas for the imagination. Yet despite their prominence in both science and culture, black holes remain shrouded in mystery, their secrets locked behind an invisible veil known as the event horizon. Among the most revolutionary ideas in modern astrophysics is the concept of the information paradox, which has sparked intense debate and driven much of the theoretical work on black holes in recent decades. According to quantum mechanics, information about the physical state of a system is never truly lost. Yet when matter falls into a black hole, it appears to vanish beyond the event horizon, taking its information with it. In the 1970s, physicist Stephen Hawking introduced a groundbreaking idea: black holes are not entirely black. Instead, they emit a faint glow of radiation, now known as Hawking radiation, due to quantum effects near the event horizon. Over immense timescales, this radiation could cause a black hole to evaporate entirely, leaving nothing behind. But if a black hole evaporates, what happens to the information it consumed?
This question lies at the heart of the information paradox. Hawking's discovery of black hole radiation was a seismic shift in our understanding, merging the principles of quantum mechanics with the classical framework of general relativity. His work suggested that pairs of virtual particles and antiparticles form near the event horizon, with one falling into the black hole and the other escaping as radiation. This process reduces the black hole's mass over time, leading to its eventual evaporation. However, the radiation itself carries no information about the matter that fell into the black hole, implying that the information is lost forever, a violation of quantum mechanics' core tenets. To resolve this paradox, physicists have proposed several intriguing theories. One prominent idea is the holographic principle, which suggests that all the information within a black hole is encoded on its event horizon, much like a hologram projects a three-dimensional image from a two-dimensional surface. This concept, developed by physicists like Gerard 't Hooft and Leonard Susskind, posits that the interior of a black hole is not as crucial as its surface. The event horizon, in this view, acts as a kind of cosmic ledger, preserving all the information about the matter that has fallen in. The holographic principle draws inspiration from the study of black hole entropy, which measures the number of possible microstates a black hole can have. Surprisingly, this entropy is proportional to the surface area of the event horizon, not its volume, suggesting that the information is stored in two dimensions rather than three. Building on the holographic principle, the ADS-CFT correspondence, proposed by physicist Juan Maldacena, offers a framework for understanding black holes in a new light. This theory suggests that a black hole in a particular type of spacetime, anti-de Sitter or ADS, can be described by a quantum field theory on its boundary, a conformal field theory, CFT. In essence, the complex three-dimensional physics of a black hole can be mapped onto a simpler two-dimensional system. This duality has profound implications, as it provides a way to study black holes using tools from quantum mechanics, potentially resolving the information paradox by showing that information is never truly lost, only encoded in a way that is difficult to access. Another tantalizing theory is the idea of firewalls, a controversial proposal that emerged in 2012 from the work of physicists Ahmed Almareri, Donald Mariloff, Joseph Polchinski, and James Sully, collectively known as AMPS. They argued that if information is preserved on the event horizon, as the holographic principle suggests, then the region just inside the event horizon might be far more violent than previously thought. Instead of a smooth transition into the black hole's interior, an observer crossing the event horizon might encounter a blazing wall of energy, a firewall that incinerates anything passing through. This idea challenges the classical view of black holes, where an observer would notice nothing unusual at the event horizon, due to the principle of equivalence in general relativity. The firewall hypothesis remains contentious, as it raises as many questions as it answers, but it underscores the deep tension between quantum mechanics and general relativity.
The information paradox and its related theories have also led to speculation about the nature of space-time itself. Some physicists, including Eric Verland, have proposed that gravity, and by extension black holes, may not be a fundamental force, but an emergent phenomenon arising from the entanglement of quantum states. In this view, the structure of spacetime is a manifestation of quantum entanglement, and black holes are regions where this entanglement reaches its maximum. This idea, known as emergent gravity, suggests that the information paradox might be resolved by rethinking the very nature of the universe's fabric. Beyond the theoretical realm, observational advancements have brought black holes into sharper focus, providing new data to test these ideas. In 2019, the Event Horizon Telescope collaboration achieved a historic milestone by capturing the first image of a black hole's shadow, the silhouette of the supermassive black hole at the center of the galaxy M87. This image, showing a glowing ring of gas and dust surrounding a dark central region, confirmed predictions from general relativity about the appearance of black holes.
The EHT's observations have since expanded to include the supermassive black hole at the center of our Milky Way, known as Sagittarius A star, further validating our models and offering clues about the behavior of matter near the event horizon. Gravitational wave astronomy, pioneered by the Laser Interferometer Gravitational Wave Observatory, LIGO, and Virgo collaborations, has also transformed our understanding of black holes. Since the first detection of gravitational waves in 2015, produced by the merger of two stellar mass black holes, scientists have observed dozens of such events. These mergers provide a window into the dynamics of black holes, revealing their masses, spins, and the violent processes that occur when they collide. Intriguingly, some mergers have involved black holes with masses that fall in the mass gap, a range where black holes were thought to be rare. These discoveries have prompted new theories about the formation of black holes, including the possibility of hierarchical mergers, where black holes merge multiple times to form larger ones. The study of black hole mergers has also shed light on another mystery: the origin of supermassive black holes. These cosmic giants, found at the centers of galaxies, have masses that defy simple explanations. One theory suggests that they formed from the direct collapse of massive gas clouds in the early universe, bypassing the traditional stellar mass black hole stage. Another posits that they grew through repeated mergers and accretion of matter over billions of years. Recent simulations, incorporating data from gravitational wave detections, suggest that both mechanisms may play a role, with primordial black holes potentially serving as seeds for supermassive growth. The quantum nature of black holes has also led to speculation about their role in the broader universe. Some physicists propose that black holes could be portals to other dimensions or even other universes, an idea rooted in the mathematics of wormholes, hypothetical tunnels connecting distant regions of spacetime. While wormholes remain speculative, they are mathematically consistent with general relativity and could, in theory, exist within or near black holes. The ER equals EPR conjecture proposed by Leonard Susskind and Juan Maldacena suggests a deep connection between wormholes, Einstein-Rosen bridges, and quantum entanglement, hinting that black holes might serve as gateways to understanding the quantum structure of spacetime. Another frontier in black hole research is the exploration of extremal black holes, which have maximum spin or charge. These objects push the limits of general relativity, exhibiting unique properties that challenge our understanding of physics. For example, an extremal black hole's event horizon and singularity may merge, creating a naked singularity visible to the outside universe, a scenario that violates the cosmic censorship hypothesis, which posits that singularities are always hidden behind event horizons. Recent theoretical work suggests that extremal black holes could provide insights into quantum gravity, the elusive theory that seeks to unify general relativity and quantum mechanics. The search for quantum gravity has also led to the development of loop quantum gravity, an alternative to string theory that attempts to quantize space-time itself. In this framework, space-time is composed of discrete units, much like pixels in a digital image. Loop quantum gravity predicts that the singularity at the heart of a black hole may not be a point of infinite density, but a finite region where quantum effects prevent further collapse. This idea, known as a quantum bounce, suggests that black holes could transition into white holes, hypothetical opposites that emit matter and light rather than trapping them. While white holes remain speculative, they offer a potential resolution to the singularity problem and a new perspective on the life cycle of black holes.
As we probe deeper into the mysteries of black holes, we are also confronted with their role in the cosmos's evolution. Black holes are not isolated entities, but dynamic players in the galactic ecosystem. Supermassive black holes, for instance, influence the formation of stars and galaxies through their gravitational pull and the energy they release as matter accretes around them. The jets of plasma emitted by active black holes, known as active galactic nuclei, can heat surrounding gas, regulating star formation across entire galaxies. Understanding these processes is crucial for unraveling the history of the universe from its earliest moments to the present day. The latest theories also touch on the possibility that black holes could hold clues to the nature of dark matter and dark energy, the mysterious components that dominate the universe's mass-energy budget. Primordial black holes, if they exist, could account for a portion of dark matter, offering a solution to one of cosmology's greatest puzzles. Similarly, the accelerated expansion of the universe, driven by dark energy, may be influenced by the collective effects of black holes as their evaporation and mergers reshape the cosmic landscape. The study of black holes is also pushing the boundaries of technology and computation. Advanced simulations, powered by supercomputers, model the complex dynamics of black hole mergers and accretion disks, providing insights that guide observational efforts. Machine learning algorithms are being used to analyze vast data sets from telescopes and gravitational wave detectors, identifying subtle signals that might otherwise go unnoticed. These tools are enabling scientists to test theoretical predictions with unprecedented precision, bringing us closer to answering fundamental questions about black holes and the universe. As we stand on the cusp of new discoveries, the mysteries of black holes continue to inspire awe and curiosity. Each theory, from the holographic principle to the firewall hypothesis, represents a step toward unraveling the enigma of these cosmic phenomena. Yet, for every question answered, new ones arise, reminding us that black holes are not just objects in the universe, but gateways to understanding its deepest truths. They challenge our assumptions, push the limits of our theories, and invite us to imagine a universe far stranger and more wondrous than we ever thought possible. The journey to understand black holes is far from over. With each new observation, each theoretical breakthrough, we peel back another layer of the cosmic onion, revealing glimpses of the profound unity underlying the universe. Whether through the faint whispers of Hawking radiation, the violent clashes of merging black holes, or the tantalizing possibility of wormholes and quantum bounces, black holes remain at the forefront of our quest to comprehend the cosmos. As we continue to explore, we are reminded of the words of John Wheeler, who described black holes as the universe's ultimate challenge to human curiosity. In their darkness, we find not just mystery, but the promise of illumination, a beacon guiding us toward the next great discovery in the vast, uncharted frontier of the universe.